All right, so 2b. When we're looking at these and finding the inverse, that means I need to take my x, my y, and have them change places. That's what it means to find the inverse. So the first thing I'm going to do is write this in terms of a y. So this is going to be y equals, and everything else is going to change or stay the same. But I'm putting it with the letter y so that I can come through and say, all right, to do the inverse, I take my exact letter x and my exact letter y, and we make them change places. So I'm going to rewrite this as the inverse being x equals the quantity y minus 3 squared plus 4. Technically, that's the inverse. That is an important step right there. It is not where we stop because we don't like to have x equals equations as much as we can. We would like a y equals. So I need to solve and get y by itself. So looking at this side, getting y by itself means I need to get rid of, and working from the outside in, I'm going to get rid of this 4 first. So I'm going to start by subtracting 4 from each side. So we're going to have that x minus 4 equals y minus 3 squared. Subtracting 4 from both sides. Then I need to get rid of this square. I'm working from my outside in, trying to get to this y. So to undo a square, we're going to square root both sides. So we're going to wind up with the square root of x minus 4 equals, and square rooting this side gets rid of my square. So we're just left with y minus 3. And we got one more step to get rid or to get the y by itself, and that's to add 3. So if we add 3 to both sides, we're going to get y equals the square root of x minus 4 plus 3. Or you can put 3 plus square root of x minus 4. Either way is fine. And then since our very first step was to switch our f of x for a y, let's go ahead and switch it back to our inverse notation, where we have f inverse, so to the power of minus 1, of x is our function rule that we have, our square root of x minus 4 plus 3. I got it wrong. Here. What's up? If you can. Because ideally, yes. But honestly, depends on how the rest of the final goes, because it's one of the last questions I grade. There's only 2 questions like number 3. So let's look at A, because I want to save B for you guys to do. Let's look at A real quick. This is kind of an important one. It's very much combines what we did on number 1 with our radical rules, because we're going to simplify each of these individually and then see if we can add them together. But you simplify them first. So I'm going to do it the same way I did on 1, where I'm dividing them into perfect squares. So I can rewrite 8 as 4 times 2 times x. And I do that because 4 is a perfect square, so we'll be able to pull that out. On the right-hand one, it's very similar. I'm going to find a perfect square in 18, which is 9. The way we write 18 is 9 times 2x. So again, simplifying each of these, square root of 4 is 2. And then my 2x is going to hang out inside. On my purple one over here, square root of 9 is 3. And that 2x stays inside. Can I simplify this further? 2 square root of x plus 3 square root of 2x. Yeah. If what's under the radical matches, we can combine these together. Because this is 2 things plus 3 things. 2 square root of 2x's plus 3 square root of 2x's. They're things, they're just really weird things. So if I have 2 things plus 3 things, how many things do I have? 5 things. 5 square root of 2x. So we can only add them together if they're the same under the radical. So if this had another piece and it had like plus 2 square root of 3, I could not add that in and it would just be listed over here. I could not add that in because it doesn't have the same under the radical. I'm just putting that in as an example. Like, you don't have to include that. Okay, so you cannot add them together unless they have the exact same under the radical. Yeah.
Can you do 4a?
4a. Yeah. So this is looking at our Module 7 stuff. So this is probably going to be something we're going to want to have those equations on that reference page, where we're going to have that, because there are 3 equations in this question. Are compounded annually, which we could argue would do the same equation as this, and compounded continuously. So I'm going to actually use our compound interest formula, which if this is not something you can pull up, you might want to have it on your reference page. This is our A equals P1 plus or minus R over N to the NT. So we need to see our story here, and we're going to find all of our pieces. What is the P in this story? 6,000. The starting amount, our principal balance. What is our R? 5.75%. When we're putting in our equation, how are we going to write it? As a decimal. What is our T? Oh, let's read that too. No, I'll keep that as purple. What's our T going to be? Time. Read the story. 9. 9 years. And we're going to start by looking at annually, which means what is our N going to be? 1. So N equals 1. So you can still use this compound formula even if we're looking at annually. If we were doing something like weekly, what would our N be? How many weeks are in a year? 52. How about this one? What if it said monthly? What's our N? 12. I'm going to say monthly more commonly, but it might be helpful to know that we have 52 weeks in a year. So looking at A, we're going to take all this info and we're going to substitute it into this equation. So we're going to start with A equals our principal, which was $6,000. 1. And then we have to make a choice. Are we going to be using plus or are we using minus? How do we know? Because it says paying, which means it's giving us money. It is increasing the balance. If it's going up, we use the plus. If it's going down, we use the minus. On the fraction, we're going to put our percent as a decimal. How do we put 5.75% as a decimal? Uh-huh. 0.0575. It scooches 2 to the left of that decimal place. We've already said our n is going to be 1. So then I have my n of 1 and my exponent as well, times my t of 9. So our n's are going to be the same. And we can absolutely use this formula with n of 1. Totally fine. And then we're going to type this sucker in the calculator. And you can, at this point, exactly type it in the calculator exactly as it is. You can simplify stuff. I can, whoa. My thing just changed pages. There we go, over here. Yeah, I know, now you're freaking out. Hang on a second. There we go, now we're back. So we can type this into the calculator, and I'm going to go ahead and pull that up just so we can practice that. So typing this into the calculator, we're going to put our 6,000. We can put our parentheses, 1 plus, that's a minus, that is not what I meant, plus the fraction of 0.0575. Oh, hang on, mine's got a weird setting thing going on. Let's fix it. Second, reset 2. There we go. If your calculator does a weird like that, let me know and I can fix it for you. So again, 6,001 plus the fraction. There we go. 0.0575 over 1. Close the parentheses. Raise it to the power of 1 times 9. You can just straight up do it like this and hit enter. We should get $9,923.72. With money, we're always going to round to the nearest 2 cents, or nearest 2 decimal places for cents. So our answer down here is going to be $9,923.72. In B and C, the only thing that changes is our n values. Part D is a different formula entirely. Our continuously compounding is taking all these pieces and breaking them up into even smaller chunks, and it uses a different equation. This is our amount in our account, PERT, P times E to the power of RT. So our principal is still the same. My principal is still at 6,000. That's not the highlighter. My rate is still the same. And my time is still the same. And E is a button on the calculator. So we need to be able to use both kinds of equations here. Or both formulas. So plugging in the pieces we have, we wind up with our 6,000 e to the exponent of our 0.0575 times our time, which is 9. So it's the same pieces, just in a very different order. And again, I'm going to show you where to find E on the calculator. I'm going to clear it out. We're going to put our 6,000. To get E, we hit the second button. So hit that green one in the top left. And then we hit our LN, that natural log button. It gives us our E and kicks us up right into the exponent. So we can just keep typing our 0.0575 times 9. And I get $10,066.96.7. We're going to round this to the nearest cent. So this 7 is going to make it up, so we're going to say 97 cents. So our continuously compounded amount is $10,066.97. The other two in this are just kind of replugging in with different n values. So I'm going to leave those ones for you to practice. Yeah.
Is the one where we didn't compound it, but we still did that equation, is that gonna be on the test?
The kind of basic interest,
Yeah.
it easily could be. Question 7 uses that for sure in the review. And question 8, all it is the same formula without any n. So there's no n piece. Yeah, so 7, 8, and 9 all use the kind of basic formula where we don't have n in it. So I'll write that formula over here just so we have it. 1 plus or minus r to the t. So that's the kind of basic one, but it's filled out the exact same way. So you're going to find the pieces you know, and we're going to solve for stuff. So it uses this formula in a very similar way to the ones we just did with our compounding and all that jazz. So I think the only really next different one, I think if we look at 5 and if we look at 10, those will kind of cover everything. And then I'll give you guys the rest of the time to work, because I want you guys to do it mostly yourselves. Because you can do this. So this is something, we haven't talked about it in a long time. This was something we did, again, way back in chapter 7. So looking at our exponential growth here, and we're looking at how f of x, our parent function here, was transformed into this piece. And we have two options. We can either notice that the graphs are the very, very same if the x's are negative. So one of the ways we can write this is 10 to the minus x. And then if we think about our exponent laws and what that means, 10 to the minus 1 is really a fraction of 1/10 to the x. So to get to g of x, we either need to make my x's negative by taking 10 to the minus x, or realize that this is a reciprocal function of 1/10 to the x, a fraction. And that's how we get a reflection across the y-axis. This is the only time we had a reflection across the y. Everything else has been over the x-axis. Oh, I just wrote that one out. Y-axis. The only way we can get a reflection over across the y-axis is to have the minus x, or by making our base change to a fraction. Which one of these, F or G, is an example of decay? So here's F. I'm going to call that one, that's purple. And G goes like this, my green. Which one of these is decaying? Is F getting smaller as it goes? Because if you think about a pumpkin that decays, it goes shrivel, 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 and it gets smaller, 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 and turns into goo. So is this getting smaller, 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 smaller as it goes? No. So which one of these is going to be decay? G of X. G of X is decay because it gets smaller. Hi.
How are you?
Doing good. How are you? Thank you, my dear.
Welcome. I can't knock that loud. They were busy.
It's okay. You knocked loud enough because a lot of times they'll come up and they'll just go. I'm like, you didn't hear me knocking? No, you were barely poking the door.
Oh, that is too
So that gets them to actually knock. It used to be Hogwarts, but I had too many kids that said, "What's Hogwarts?" And it hurt my heart, so I have surfing cat.
I like the surfing cat.
There you go.
See you later.
See you, my dear. All right. So these are not things that are going to come up super in depth. We are not going to have to know any more than that at all. And honestly, if we just catch these two, that covers most of it. And then let's look at 10, because that lets us practice our transformations and all that stuff as well. So at least be our last piece. We've been working with these a bunch. Does anyone remember what these are called? These kinds of functions? What kind of function is this? An exponential. So when it says what type of function, I'm looking for, is it linear? Is it quadratic? Is it exponential? Is it logarithmic? Is it rational? So this is an exponential. And the way we can tell looking at our equation is that my x is in the exponent. So it's an exponential equation because my x is in the exponent. Looking at this exponential here, I'm going to pop over b for a second because I want us to identify our transformations first. That will help with b. But that means I need to know my transformation form. And for an exponential function, I'm going to write our transformation form up here. So we're going to have our f of x. That's our a times b to the x minus h plus k. So what is our a value for this function? 3. What does an a of 3 do as a transformation? It's got a vertical stretch. That gives me this one. What is my h? -1. So my h is -1, which means which direction did it go? Left 1. How about my K? -2. Which means what transformations did it have? It went down 2. Oh, I love that. It's not quite the right picture. Fantastic. So now we're going to look at B, and we're going to look and say, what kind of asymptote is this going to have? A vertical one or a horizontal one? What kind of asymptote did these have? You could look at the picture here. What kind of, yeah, it has horizontal. It's going to be right around here. So we know it's going to have a horizontal asymptote. And when we write horizontal asymptotes, that tells me my y is stuck at a value. So my equation is going to be a y equals. What is y going to equal? I was like, look at our equation. Negative what? Don't look at the picture because the numbers are labeled weird. Look at our equation and what we have there. -2. Y equals k. Just like it was in rational functions, x equals h, y equals k. But this doesn't have a vertical asymptote. It only has a horizontal. What is our domain? What are our x values that work? That would be if we had, you're thinking more excluded values. So this is saying which x values work. Where can I go and find a point on my graph? Is there anything that's stopping me as I go here? Are there any asymptotes over here? Nope. So I can go all the way from negative infinity. How about to the right? Are there any asymptotes stopping me over here? Or walls or anything stopping? Nope. So we can go from negative infinity to positive infinity. Other way of saying it is all real numbers. Both of those are fine. So then we're going to look at our range. Remembering we're kind of keeping an eye on the actual numbers, not the numbers on the picture. What y values do we land on? Yeah, it's going to be -2 and bigger, right? So our range is going to go from -2 as the smallest possible value to infinity. Your algebraic way of writing this is that my y has to be greater than -2. When it's an asymptote, it actually can't equal, so I'm going to just put greater than. Because remember, I can't go through the walls, or I'm going to have to start throwing myself at cabinets again. Okay, so that's all the different kinds of equations in 6 and 7, all the different kinds of problems in 6 and 7. Tomorrow we will go through probably 8 and 9 so that we can Monday kind of do kind of an overall, because 10 is the one we just did. So tomorrow we'll probably try and work through as many in 8 and 9 as we can. That way you're getting a chance to get this, for the most part, finished up before next week. The answer key is posted up on the Canvas page. So as you're working through stuff, if you're stuck on something, don't know where to go, don't know what happened or whatever, the answer key's up on Canvas. It's there to help you, to let you do the thing. You have about 8 minutes until the announcements start.